Hi and welcome to the second of our videos on how to approach a problem solving and modelling task. In this video we'll look at the ladder problem. So a window is 12 metres off the ground and we want to explore the different lengths of the ladder, or that the ladder could be to use a window, if the angle of the ladder to the ground must fall between 30 and 40 degrees. Now obviously at 30 degrees our ladder's got to be a bit longer than it does have to be at 40 degrees, but how much longer and what happens between 30 and 40. So just a reminder, the problem solving flowchart is a 4-step flowchart and you need to address each of those steps in order to unlock the marks associated with them. That is, if you omit one of those steps you also lose out on the marks. So let's look at these. I've broken the problem down already. You'll see in red the various subparts and in black my responses to them in relation to this particular ladder problem. So if we were to define the problem mathematically, in regards to the ladder problem, I might consider that as a right angle triangle that has a side, the opposite side, and an angle given, but it's missing the hypotenuse. I could identify some assumptions and variables. So the variables might be the angle that we change it at progressively from 30 to 40 degrees, and we change that so it's independent, and dependent upon that is the length that the ladder needs to be. So there's our two variables. Assumptions I've made are that the ground's level, we're dealing with a vertical wall, that the ladder is rigid and won't flex, and I'm thinking that 1 degree increments are okay. So I'll go from 30, 31, 32 right the way through to 40. I'm also going to have consistent positioning of the ladder, and I'm not going to use move the foot of the ladder at all. It will remain fixed on that same spot and I'll just change the length of it. So it looks as though trigonometry, particularly sine, will help me here to find the length of the ladder between 30 and 40 degrees with the horizontal. So that's my initial plan. So we move on to the solve stage. So I'm going to select and apply now, and I'm going to use the opposite side value of 12 meters and start at 30 degrees and calculate the length of the hypotenuse using sine equals opposite over hypotenuse. And once I've done that once, I'll increase my angle from 30 to 31 degrees and recalculate it and do it again for 32, 33, right through to 40. You'll notice straight up that this is the same calculation performed 11 times. So within my report, I would probably show the first calculation, and then rather than filling up quite a lot of information in my report, I perhaps repeat the calculations in the appendices and show the additional 10 calculations there and tabulate them. Make a table in my report which summarises my findings. Now there's many possible approaches that we can use. I'm not going to actually make a model for this. I'm not dealing with data, so I won't generate or test hypotheses. I am, however, using a fairly standard mathematical technique in trigonometry. So with the solve there, I might need to revisit the assumptions and observations. So what happens if the ground isn't level? Or what happens if, as people get on that ladder, it actually flexes and bends? Obviously, if it's not in a straight line, my ladder might need to be a little bit longer. So I might need to refine my model. So here, solutions, as I said previously, could be found in a number of ways, and I'm going to use the trigonometric methods here. And it's appropriate to use both a spreadsheet and a scientific calculator. So the spreadsheet will actually automate some of those repeated calculations I referred to before. So to evaluate or verify my solution, remembering that this is important, I can't just come up with a solution and assume it's correct. I've got to show it to be reasonable. So how can we check the accuracy of these calculations? Well, I might, if I wanted to, determine the other side, the adjacent side, and then maybe use a bit of Pythagoras to just confirm. I might just substitute back in my length of my ladders in to see if it actually will, in combination with the 12 meter height, if I come back to the angle that I was first looking at. So just checking that my calculations are reasonable. I should also determine the strengths and limitations of my model. And the strengths here, well, trigonometry is a really well established and accurate process. It's quick and relatively efficient. So that's a couple of real key strengths to this model or this solution that I'm presenting. The limitations, however, and these reflect back to the assumptions I made, is that my model or my solution only applies to flat ground and vertical walls, so basically right angle triangles. So in real life that's probably not always going to be the case. So how am I going to actually improve my model? Might be if I looked at some ways to actually address those shortcomings. I'm also assuming that the starting point from the wall is fixed, and I'm always putting the foot of the ladder at the same spot in the earth. So, if I was to make refinements, and recall that refinements are important, I should be showing a progression in my complexity of my model to get a good finished product. So I might then go off and investigate the different distances from the wall. What effect might that have? So rather than actually keeping my foot of my ladder stuck in the earth at one spot, what happens if I shifted it elsewhere? What would be the outcome there? What happens if I allowed for a flex in the ladder, say of 5%? What would that do, and how would I account for it in my model? And I could, if I wanted to, investigate non-right angle triangles, so where the wall wasn't perfectly straight, upright, or the ground wasn't level. So refinements there could increase the complexity of my solution and also improve my mark overall. So remember, problem solving, mathematical modelling, these tasks are not linear, and they normally involve a process where you look at what you've done and look to refine and perfect it. Okay, and so finally, to communicate these things, remember this list that we should go through, and it might be worthwhile pausing and jotting these down, but the list that we go through here. Now, in order to do it, to communicate well, I tend to think of it as these 4 steps. I would define the problem, I would present my solution, I would then evaluate and verify and provide some conclusion. And I'd be more than happy if I was a teacher to read those as subheadings: the problem, the solution, evaluating and verifying, and conclusion. Now remember, it's got to be a unique response, so you can respond any way you like, but you really should address those 4 different areas. So I hope this has been of some benefit, even in helping with this particular task, but also in adapting it and using it in other tasks. Good luck with it, and we'll see you later.